So, hi everybody. Um, Last time it was supposed that we finish the topic compactness, and we actually have done it. But there was a question which I think I would like to answer, and also I have realized that I have used not quite ideal notation, so I need to clarify the notations I used. So what we have done last time, we have discussed compactness criteria in this space. And so I want to stress what is it. So this space is the space of all real valued Borel measures on X, which endowed with this variation norm. And the statement was that this is a Banach space with this variation norm. So once again, so we take a real valued Borel measure on X. We find its Han-Jordan decomposition. So this is a difference of two non-negative and bounded Borel measures. So then we construct this measure is a sum of these two parts. And then we consider this norm, so this mapping, so mu. So we calculate this measure mu at this set, so mu of the whole space X. And this is called the variation norm or total variation norm. So this is the space of all real valued Borel measures on X whose variation norm is finite. So I would say that better notation would be if I use not mu of X but mu B of X. So to emphasize that we consider bounded measures in the sense that their total variation norm is finite. Also, I have used this notation, and by this notation, I mean a subset of this space, which consists of non-negative measures. That is, this as it is a subset of this set, it is the set of finite or bounded non-negative Borel measures on X. So I use finite or bounded as synonym. And again, better notations would be mu b plus of X. So depending on literature, people use such notations or some other notations. No matter what the notation is, we should understand what is meant under this notation. So yes, so I have to stress that I meant the bounded measures. And of course, if we consider probability measures, they are a subset of this set. But of course, if I want, for example, to consider Lebesgue measure on R, Lebesgue measure on R, then of course this Lebesgue measure is not bounded. So sometimes it's worth to consider not only bounded measures, and then this is the sign for all Borel measures, not non-negative Borel measures, not only bounded. So that's why my notation was misleading. But nevertheless, I have clarified what I meant under these notations. Okay, so we keep on considering this set. And we have specified that in one hand, it is a Banach space with this norm. But on the other hand, there exists also a weaker topology, which is weaker than the topology generated by this norm. And this topology, the convergence in this topology, the convergence of a sequence in this topology can be characterized in this way. So a sequence of measures converges weakly to this measure if and only if for every bounded continuous real function f, we have this convergence of integrals. Okay, so we have specified the very important theorem, the compactness criterion in this space. Or better to say relative compactness criteria. It's a Prokhorov theorem. So every sequence, so the following two conditions are equivalent. Every sequence mu n contains a weakly convergent subsequence. This is the statement which is equivalent to relative compactness of the set M. I have added the link, so we have discussed this theorem. I guess it was lecture number 4. Let me try to find it. Sorry. Sorry. I'm not that fast. Yes, so this is it. So the set, so if we are in the metric space, the following conditions are equivalent. So the set is a given set is compact, and every sequence of elements from K possesses a subsequence converging in K. So if set K is relatively compact, that is its closure compact, then then it is equivalent to the statement that every sequence of elements from K possesses a converging subsequence, a subsequence which converges somewhere, but then if we take closure, and then the sequence would converge in K. So having this in mind, we see that this is the statement equivalent to relative compactness of the set M. And the statement of the Prokhorov theorem is that this condition is equivalent to this condition, and this condition is that the family is uniformly tight and uniformly bounded in the variation norm. Okay, so this is what we have discussed last time, and then there was another special case. So this is the theorem when X is just a complete separable metric space. But in the special case of RD, there is also the Levy theorem that a sequence of probability measures. So we have RD and a subspace of M, subset of M, a set of probability measures. So a sequence mu n of probability measures on RD converges weakly precisely when the sequence of their characteristic functionals, that is Fourier transforms, converges at every point, and the function phi, which is the limit, pointwise limit of all the Fourier transforms. Yeah. So this the sequence of Fourier transforms converge at every point. So there is a pointwise convergence. Hence, there is a function, we can define the function, which is the pointwise limit of these functions. So the requirement is that this function is continuous at the origin. In that case, phi is the characteristic function of a probability measure, that is the limit of the measures mu n in the weak topology. And then something similar, but not for a sequence, but for a family of probability measures. So there was a question why continuity at origin, only at origin is considered, and why it is sufficient. So why the origin is so important. As I said, the answer is not that fast, but I have decided to answer this question because by answering, we have to discuss some important things, which are usually not discussed neither in functional analysis nor in measure theory. So, but it's still important information for those who are interested in measures and functions, functional analysis, probability, etc. Okay, before I want to stress that I also have realized that I have used two different notations for Fourier transform. When we discussed compactness criteria in LP, I used hat for Fourier transform, and here we have tilde, but both notations are a kind of standard notations for Fourier transform. So I'm sorry I didn't specify it, but now I stress that so here we use the Fourier transform. So this tilde or hat, no matter how I denote it when I say about characteristic functions or for Fourier transforms, it is the same. Okay, so now the answer to the question. I use this. So this is a reference where you can read the answer to this question in a nice manner, and this is also a chance for me to advertise this book. So it's a book of Niels Jakob, Pseudo-Differential Operators and Markov Processes. There are 3 volumes of this book, and the volume 1 is about Fourier analysis and semigroups. And actually, it's a very nice book. I like all 3 volumes. It is worth to have this book in your library and address it when you have some questions. So there you can find. So here you can find the answer presented in a very reader-friendly manner. Also, the answer can be found in the standard reference, Bogachev measure theory, but the answer is somehow spread along two volumes. Okay, so now the answer. In order to answer this question, we need to understand what are these functions, Fourier transforms of probability measures. What are they? And for that, we give a definition. So a function phi from Rd to C is called positive definite if for any choice of natural number k, any choice of vectors u1, uk from Rd, domain of definition of this function, the following matrix is positive Hermitian. What does it mean? This means that for any choice of complex numbers, lambda 1, etc., lambda k, we have the following statement. So how to understand the statement? So we may denote this matrix as A. This is a matrix of the size k times k. We have also this. So this means that we may consider a vector lambda. This is a vector with coordinates lambda 1, lambda k. So this is a vector which belongs to ck. And then what is written here, it is just A applied to lambda, scalar product with lambda, and this scalar product in the space ck. So this complex conjugation, it is just because we take scalar product in ck. So I recall that if we have C, then scalar product in C is just x times y bar. And the same story coordinate-wise in ck. Okay, so this is the definition. Example, let us consider probability measure on Rd. Then its Fourier transform or characteristic functional is a positive definite function. So exactly satisfies this condition. So here I have written all possible notations for the characteristic functional of a measure mu. So either this one, or Fourier transform with tilde, or Fourier transform with hat. I'm sorry, just once again, all the notations are about the same object, which is given here. So the statement is that this is a positive definite function, and let us check it. We should check that this holds for any choice of k, u's, and lambdas. So let us do it. So we take a sum, ij from 1 till k. I take this phi mu of ui minus uj, lambda I, lambda j bar. It is. Now I insert what this guy is. This is this integral. And of course, integral and finite sum, we can interchange them. Wait a minute. Okay. So this is equal to, sorry, integral Rd over Rd. Then inside the integral sum, ij from 1 till k. Then lambda I, lambda j bar, and then exponent of I x dot, this dot, so I have not specified this, but this dot, I use this dot for notation of the scalar product in Rd. So instead of these brackets, I use just this dot. And here again. Okay, and here we have ui minus uj. And then mu dx. Or, yes. So probably I should make y and here y. And also probably I should to make everything totally nice, I have to put y at the end. Yeah, so something like this. And now we use the properties of exponential function that exponent of a sum of two things is product of exponents. That's why all this we can, of course, rewrite in the following way. This is the integral over RD. Then sum, let me say j from 1 till k, lambda j. No. Let me make I. Oh. I from 1 till k, lambda I, e to the power I, u I times y. This is one sum. And then another sum, j from 1 till k, lambda j, e to the power I, u j times y, and then bar goes here. And then mu dy. And then you see that this is just a product of a vector time, a complex number times its complex conjugate. So this is the absolute value of this number. So this is the integral over RD, absolute value of this guy. Mu dy. And then you see that this is non-negative, and hence the integral is also non-negative. So we have shown that this inequality holds for arbitrary k vectors u1, uk, and lambdas, lambda 1, lambda k. So we have shown that characteristic functionals of probability measures are positive definite functions. But as you see from the all the proof and from this formula, so the Fourier transform exists not only for probability measures but for bounded measures. And so we may state that for any bounded Borel measure, its Fourier transform is again a positive definite function with the same proof. Okay, is it clear so far?
Yes.
Yes, I have one small technical clarification
Yes.
question. So when we call it a characteristic functional, so functional is a mapping that takes a function and outputs a number. Yeah, and when we look at a characteristic function, it seems like it's just a function. Yeah, so it's
okay.
we
About
have
my notation
x and have another number.
Yeah. So actually, generally speaking, such words as function, mapping, functional, operator, these are roughly speaking synonymous. And then if one wants to specify the domain of definitions of all these mappings, then there is a difference.
I try to think about it, and maybe if we consider our mu to be a measure with a density, then we can view this as a functional that takes this density and outputs a number, and then it's like formally a functional, like
Yeah, so I use this notation terminology functional, characteristic functional because because my standard reference was Bogachev measure theory, where measures on topological spaces and measure theory on this level of generality is considered, and there it is called characteristic functional. So since it was the main reference, which it is supposed that you also use it, I use this notation as in the book of Bogachev. But of course, in this case, it is characteristic function, standard terminology, and you don't need to think more about this. So yes, so I'm sorry, I should keep it function, but it was just to follow the terminology of Bogachev.
Thank you.
So there is nothing more behind. But of course, you are right. Yes, you may consider it as a more advanced mapping if you take the density of this measure and consider it like the mapping of the density to something else, to another function. Okay, so if we have a Fourier transform of a bounded Borel measure, it is a positive definite function. Moreover, there is a very important result, which is called Bochner theorem, which states that actually a function phi is the Fourier transform of a bounded non-negative Borel measure mu on Rd if and only if it is positive definite and additionally continuous, and phi of 0 is nothing else but the measure of the whole space. So if and only if. This direction is, roughly speaking, obvious. We have shown it already. That is, if we have a Fourier transform of a bounded measure, we have shown that this is a positive definite function. From the formula, you may see that it is easy to show that this function is continuous with respect to x. So this function is continuous. And also, if we consider phi of 0, yeah, so phi mu of 0 is then just integral of 1 mu dy, integral over Rd, and this is nothing else but mu of Rd. So this direction is obvious, and all three conditions are very easy to verify. The opposite direction is non-trivial, and we are not going to show it, but this is a very important result, that for any function of this type, there is a measure, a bounded non-negative Borel measure, such that this function is its Fourier transform. So please remember this theorem. It is an important result. Okay. So now let us go further, and we need to discuss some properties of positive definite functions. Since this is an important class of functions, let us discuss them a little bit in more details. So this is the definition. In this definition, we take a particular choice of k. So we take k equal to 2. Particular choice of vectors. So u1 is equal to 0. u2 is just some vector in Rd. And hence, what does mean that the corresponding matrix is positive Hermitian? So the matrix looks as follows for this choice. The corresponding matrix, this matrix looks like this. So it should be Hermitian. This means that this guy is complex conjugate to this guy. So this is what is written here. And it must be positive. What does it mean? Positive means that all major minors should be non-negative. What does mean major minors? This is the first major minor. It should be non-negative. So this is the first requirement. And then the second non-negative, second major minor should be non-negative. That is, the determinant of this matrix should be non-negative. That is, determinant of this matrix, let me call it A again. So determinant of A, what is it? This is phi square of 0 minus phi u times, and we use this identity already. So times phi bar u, it should be non-negative. But what do we have here? This means that phi squared u is bigger or equal than absolute value of phi of u squared. And hence, we arrive to this inequality. Positive definiteness of the matrix imply these two things. Let us remember these inequalities. May I go further?
Yes.
Okay, second statement. The set of all positive definite functions is a convex cone which is closed with respect to pointwise convergence. So convex cone means that if we have a positive definite function phi and multiply with a positive number, we get again a positive definite function. And also if we have two functions which are positive definite, and their sum is also positive definite. Or we may say that linear combinations with positive constants, positive scalars, linear combinations of positive definite functions are positive definite. It's very easy to check because you just look at this inequality. So if you, instead of phi, you have lambda phi for positive lambda, this change nothing. And if you have the same for phi and for psi, then the sum, so if this is positive and the same for psi is positive, then the sum of, that is, if you consider psi plus phi, such sum will be also not positive, not negative. But I hope you understand that it's obvious in a sense that the set of positive definite functions is a convex cone. And again, and the second statement, which is also obvious, that this set is closed with respect to pointwise convergence. Again, if we have a sequence of phi n which converges to phi at any point x in Rd, so if we have all these guys positive definite, so we have these inequalities for all n's, and then we go to the limit. And yeah, so if we have inequality before limit and then we go to the limit, the inequality will be preserved. Okay, so I hope that this is clear, this property too. Agree?
Yes.
Yes, we go further. The following inequality is true for any positive definite function. So phi at any point u1 minus phi at any point u2, absolute value squared, is smaller or equal. And on the right-hand side, you see phi of 0 times, and here in the brackets, phi of 0 minus real part of phi of this difference. So this is an exercise to show this. As we proceeded here we consider k equal to 2 and u1 is equal to 0 and u2 is something. Here you should consider k equal to 3, u1 is equal, okay, u3 is equal to 0, u1 and u2 some vectors, and playing with positive definiteness of the corresponding matrix, one can show this, but it's a technical exercise. But well, just some inequality, but here you have difference of phi in different points, and here you have phi of 0 minus phi of this difference. So if you assume, let's say, that u1 is fixed and u2 tends to u1, converges to u1, then this would be an okay, what we have here you have that this guy converges to 0, and then phi of 0 minus something, phi of something which converges to 0. And now we use so what do we have? So if phi is continuous at 0, then phi is continuous everywhere. And not only continuous, but also uniform continuous, because we have 2 points, and here everything is only here. So conclusion, if a positive definite function phi is continuous at 0, it is uniformly continuous on Rd. From this inequality. So any 2 points with small distance between them, then this difference can be estimated via this stuff. And here we have only 0, 0, and difference between 2 points. Not difference, distance between 2 points. Sorry. Okay, so these are 2 important properties. What else? So we are coming back to our theorem, Levy theorem. So we consider only part 1. So I repeat this theorem. A sequence μn of probability measures on Rd converges weakly, precisely when means if and only if. The sequence of their characteristic functionals converges at every point, and the function which is this pointwise limit of Fourier transforms is continuous at the origin. In that case, phi is the characteristic function of a probability measure mu. that is the limit of the measures mu n in the weak topology. So let us prove the theorem. In the right, so in this, so this precisely then, this is if and only if. So let us prove this direction. That is, we assume that the sequence of Fourier transforms of probability measures converges at every point. So let mu n be a sequence of probability measures such that their Fourier transforms converge pointwisely to some function phi, which is continuous at origin. Then, so this function phi is a pointwise limit of positive definite functions. Hence, this function phi is itself positive definite. Moreover, since we assume that phi is continuous at origin, as we have just shown here, the function phi is then uniformly continuous, but in particular continuous on the whole space. And this also holds because, yes, because all mu n's are probability measures. That is mu n of Rd is 1. Hence, this is also mu n tilde of 0. So this is a sequence, mu n tilde of 0. It converges to 1, which is phi of 0. So we have this identity. So from this assumption, we have this, and then we use the Bochner's theorem. So if we have a function phi which satisfies these three conditions, then there exists a measure mu, non-negative bounded Borel measure mu, whose Fourier transform is given by phi, and then phi of 0 is equal to 1, and this is mu tilde of Rd. This is mu of Rd. So we see that mu is a probability measure. Okay. So under this assumption, we obtain that there is a measure, a mu, such that its Fourier transform is exactly this limit. This is not all. We have to show that this mu is really the weak limit of the measures mu n. And this is not that trivial. So one shows that, so we use an Prokhorov theorem, and instead of showing that mu n converges weakly to this mu, exactly this mu, instead of that, one shows that this family is uniformly tight. And for that, one needs more additional technical things. And that's why I would like to show you this corollary. It is corollary 3816 in the book of Bogachev, and it is again an interesting result. So for any probability measure, mu, and for any strictly positive number r, the following inequality holds. So what is here? So here we have mu of some set, and here we have mu tilde. This is the Fourier transform of this mu. And so what do we have here? So if r is very small, then r to the power minus 2 is very big. So this is the outside, so outer of a very big ball with centrum at 0 and radius r to the power minus 2. So this is so like a complement of a compact, and this compact is a very big ball with this inequality. Okay, complement, I mean, okay, with this, one should be careful with this, but relative compact. Okay, so if r is very small, this r minus 2 is very big, but here this is something very small. And this is a ball around 0 with this radius, so it's a very small ball. So since this mu tilde is a Fourier transform of a probability measure, it is a continuous function, and particularly this function is continuous at 0. So choosing r very small, we can make this supremum also very small. So we can, playing with r, we can find sufficiently big relative compact, that is the ball with radius r minus 2 with centrum 0, so big compact, such that outside this compact the measure is, so the measure of all the rest is arbitrarily small, so we can choose it. So this inequality holds for this mu and also for all of these mu's, yeah, with their own suprema here. And now one should use that mu n converges, mu n tilde, so these functions converge pointwisely to the function phi, which is mu tilde. And one also can prove that if we have a pointwise convergence of Fourier transforms of measures, then this convergence is actually also locally uniform, that is uniform on compact sets. And hence, playing with this, so using this corollary and having this result that mu n tilde converges to mu tilde locally uniform, one can show that the family is uniformly tight. We are not going to write down it or clarify all technical details, but the idea is hopefully clear. And this inequality is also a nice result. It's nice to know it. Okay, so we have shown the statement in one direction, and in the opposite direction, everything is actually obvious. So may I go to the opposite direction?
Okay, please.
Yes. So this is not the proof, it's like ideas of the proof. Yeah. So this is not that easy technically, but all the needed items are specified. So this inequality plus local uniform convergence of this family, this sequence of functions to this function.
Can you please go back to the previous slide for a second? And once more. So in this handwritten part, we have that mu n tilde of 0 goes to phi of 0, right?
Yes, yes.
So we don't know that this is so I mean, like, we can write that 1 is equal to mu n of
Okay,
0, which
let me
goes
write down
to
like this.
yeah, and
Yeah.
from this we have that phi of
Yes,
0 is
yes,
1.
yes, yes, yes.
Thank you.
Thank you. Yeah, so in one hand, this guy this sequence of numbers converges here. On the other hand, this is just a stationary sequence of ones, so it converges to 1. This is what I wanted to say. Yeah. Okay, so it was one direction. The opposite direction is, roughly speaking, obvious. So if we assume that mu n the sequence mu n converges to mu weakly, then by definition of weak convergence, all such integrals converge. So all such integrals converge to this integral because these functions, for every fixed x, these functions as functions of y, they are bounded and continuous. So since such functions are bounded and continuous, we have, by the definition of weak convergence, we have this. That is, we have that Fourier transforms converge pointwisely in all points. In particular, in the point x equal to 0, the left-hand side will be just one, again, once. Always, this integral is equal to 1 always for each n. So it's a stationary sequence. It converges to 1 in one hand. On the other hand, it converges to mu tilde of 0. So we have this. And hence, this also clarifies that if a sequence of probability measures converges weakly to some measure, then this measure is again a probability measure. Okay, I guess I have answered the question why the convergence at 0 was so crucial at the region, continuity at the region, why it was so crucial. And this is the last slide to chapter 2. So are there any questions? Okay. So as a summary, please remember the Bochner theorem and that Fourier transforms of measures. It's an interesting and very special class of functions with their own interesting properties, positive definite functions. Okay, now we have finished this chapter and we go further. So chapter number 3, normed and inner product spaces, orthonormal bases and projections. Well, it is supposed that you know something about normed and inner product spaces. But on the other hand, I should be self-contained, so I start from the very beginning and we just go through the basics just to remind you what is what, to check if you remember or if you know or you don't know, but it will be sufficiently fast, but I hope that it will be fine. So please stop me and ask questions if there are some of them. But again, we start from the very beginning and go fast through it. So basics, I recall, so what is our wishes? So first of all, we wanted to lift standard mathematical analysis in RD to infinite-dimensional setting. For this, we have introduced and discussed the notion of topology. So the lifting was due to this fundamental object, topology. Now our second aim is to lift linear algebra, so the results of linear algebra to this infinite-dimensional setting. And to have it, to make it, we need linear structure, first of all, and then we need combined topology and linear structure. So I recall what is linear structure. So actually, what is a linear space or vector space? So let X be a set, we have a field with two operations, addition and multiplication, and there are two operations, vector addition and scalar multiplication. So we multiply the vector, the element of the set with the scalar from the field K. So, and then this set X with two operations, vector addition and scalar multiplication, is called a vector space or linear space over the field K if for all elements x, y, z from this set X and all scalars alpha, beta from this field K, the following holds. So commutative law for addition of vectors, associative law for addition of vectors, existence of a neutral element, so zero element in the set X, such that 0 plus x is x for all vectors in X, and existence of an inverse element that for any element X from the set big X, there exists an inverse element such that inverse plus the original is zero element, neutral element. And also some conditions on the relation between scalar multiplication and vector addition, so distributive laws, standard, and then also kind of associative law for scalar multiplication. And also this condition, then unit element of the field times vector is vector itself. So everything is standard linear algebra. Okay, so linear structure, that is, we consider not just an arbitrary set X, but a vector space X. And now we define what is called the norm. So in the sequel, in this chapter, the K is just real numbers or complex numbers. So let X be a vector space over the field K. A mapping is called norm if norm of X equal to 0 may happen if and only if this X is the zero vector of the set of the vector space X. Then the second condition is the so-called absolute homogeneity, that the norm of lambda X is equal to absolute value of lambda times the norm of the X for all X and all lambdas in K. So absolute value here, the word absolute here. And triangle inequality, that norm of sum X plus Y is small or equal to the norm of X plus norm of Y. A pair X and a norm on this set is called a normed space. Remark, if X is a norm space with a given norm, then it is also a metric space. So having the norm, we generate the metric using this identity. And yeah, triangle inequality here allows to establish triangle inequality for the metric. Symmetry is obvious due to absolute homogeneity. That is that this stuff is equal to norm of y minus x. Yes, due to this property. So symmetry is okay. And positive definiteness is okay due to this. Statement. The operations of vector addition and scalar multiplications are continuous mappings with respect to this metric. And one more statement, not all metrics on vector spaces can be generated by norms. So I suggest you immediately give me some counterexample. Everything is simple. So having norm.
A discrete metric.
Yeah, so for example, yeah, so any metric which is bounded cannot be a norm, yes, due to this property. Yes, because if we take x with norm equal to 1, and then for all lambdas in the field, we should have this identity. So this guy, if lambda goes to infinity, absolute value of lambda goes to infinity, then this guy also, the norm of this guy also increases, yes? So discrete metric cannot be a norm or any other, for example, if I consider x equal to r, and distance between two elements of x is just absolute value over 1 plus absolute value. It is again a bounded metric, which is not a norm. Okay, so this is a thing which is not always true for a metric. Okay. Next definition about inner product. Again, the field is real numbers or complex numbers. We have a vector space over this K, over this field. A mapping is called an inner product if scalar product, okay, inner product. Inner product, so fine English is inner product, but we also use scalar product. Okay, so inner product of x with itself is non-negative for all elements x. Inner product x with itself is 0 if and only if x is 0. Scalar product or inner product x and y is equal to scalar product y and x if k is real numbers, so symmetry. And if k is the field of complex numbers, then when you interchange variables, you should make complex conjugation. That is, inner product xy is the same as inner product yx and complex conjugation. And also property number 4, linearity with respect to the first variable. So this linear combination inside can be pulled out, so to be outside. Okay, a pair X with this inner product is called inner product space or pre-Hilbert space. So I will use this IPS, inner product space. Okay, and additionally to this definition, if we have two vectors in our vector space, which satisfy this condition, so inner product X and Y is equal to 0, we say that these two vectors are orthogonal. And this is the notation. So everything is standard as in linear algebra. Remark, the inner product is a bilinear form in the case k is real numbers, and it is a sesquilinear form in the case k is complex numbers. What is meant by sesquilinear? So let me show it. We consider z alpha x plus beta y. So if we are here in this situation, so we interchange the variables using the complex conjugation. And now we use the linearity. So this is the property number 4, and this was the property number 3. Now we use linearity, and complex conjugation should be taken into account. xz plus beta bar yz. And then again, we use number 3. This will be alpha bar zx plus beta bar zy. So you see, in the real case, alpha bar is the same as alpha because they are real numbers. So and we get that the scalar product is linear with respect to second argument. If we are in this case where all scalars are complex numbers, then complex conjugation stays here. And this is a little bit worse than linearity. So it's like, so B linear means, so B means 2. So it's linear with respect to the first and second variable. And sesquilinear, it's like 1.5. Like it is completely linear with respect to the first variable. So it is 1. But it's not totally completely linear with respect to second. So like 1/2 of linearity with respect to the second variable. That's why sesquilinear form. Okay. I go further. I hope that everything is known. We just repeat and refresh. Okay?
Okay.
So Cauchy-Bonnikovsky-Schwarz inequality. So let X be an inner product space. Then we have this inequality for all elements xy in X. And it is also a very well-known inequality, but I think it is still worth to prove it. So let us do it. Also quite fast. If we consider y equal to 0, then it is obvious because we have zeros here and here. So scalar product with 0 is 0. And this is also 0. Then we consider the case y is not equal to 0. Then we have for any lambda complex number. Okay, let me show in the complex case, but in the real case it is the same, but you just don't need extra complex conjugations. So what do we have? We have that 0 is smaller or equal than product of scalar product, inner product of a vector with itself, and this is the vector. So what is it? I use the sesquilinearity of this inner product. So this is x times x minus lambda y times x minus lambda bar x times y plus lambda times lambda bar y times y. Okay, so this is true for any lambda, so choose a particular lambda. So this is my choice of lambda. So I can rewrite it in this way. So this is yx bar, yy. Then when I insert this particular lambda in this inequality, so this is the left-hand side, this is the right-hand side. So what do I have? I have 0 smaller or equal to x times x minus 2 times absolute value x and y, absolute value squared, over y times y plus absolute value x and y, absolute value squared. And here y times y, absolute value squared. And here y times y. So let me see. So this guy is here. Then this lambda, I use this version of this form of lambda. So this guy times this guy will give me this story. So -1, this fraction. Now here What is lambda bar? Lambda bar is, if it is lambda, I use this form, then lambda bar is just bar here on the denominator because this is something positive. So you don't need a bar here. And this again will give me the same object here. So these two guys, they just give me this -2 and then fraction. And then this is my yy, it is written here, and lambda times lambda bar, this is just, this is just a lambda absolute value squared. And this is what I have written here. So now you can subtract, and then you have -2 plus 1. So this is just then x times x minus, here we have absolute value xy squared, and below y times y. But actually that's it. We have already proved, because what do we have? 0 is bigger than this stuff. This is exactly what is written here in the case when y is not equal to 0. That is, the denominator is strictly positive. Okay?
Okay, very nice proof.
Yes, I like it. And it works in complex case. Because usually in the lectures, people consider only real case, and then there is a kind of a polynomial, second order polynomial, determinant, etc. But this works for already for this case. Okay, let us go further. May I?
Yes, please.
Okay. Remark, if we have an inner product space, then the mapping given like this is a norm on X. Again, this is an exercise for you. So the conclusion is that if we have an inner product space, then it is just a special case of a norm space. The scalar product, so second statement, the scalar product is a continuous mapping in the topology generated by the norm, which is generated by the scalar product. Again, a simple exercise for you. So as I said here, if we have inner product, we can create a norm. But not all norms can be generated by inner products. There is a special statement called parallelogram inequality, or Jordan von Neumann theorem, which states that a norm space is an inner product space. That is, this given norm is generated by some scalar product if and only if this parallelogram inequality holds. So in this parallelogram inequality, we have, let me call, so we have 0, we have, let's say, x, vector y. Then this would be, let me draw, if I'm able to, no, my drawings. Yes, so we draw a parallelogram. And you see that this is the vector x plus y, and this is this vector is x minus y. So what is written here is that so the length, two squares, these are the lengths of diagonals, squares of lengths of diagonals, this and this, is equal to the sum of squares of all sides of the parallelogram. So if this holds for the norm, then there is an inner product behind. Otherwise, there is no inner product behind. Okay, I hope that it is also known. So what do we have? So we have discussed metric spaces. Now we have discussed a special case of metric spaces, namely norm spaces. They are vector spaces or linear spaces with norm. A norm is a nice mapping which combines, which allows to combine linear structure and topology. So norm allows us to recover a metric. So norm space is a special case of metric spaces, and inner product spaces is a special case of norm spaces. Inner product is even better than just a norm because we have the notion of orthogonal vectors. Yeah, so they are orthogonal. And so this allows us to add even somehow a kind of geometry, not only linear algebra, but also kind of geometry here. So the more structure we have, the better results we can gain. But nevertheless, first of all, so metric space is a subspace of topological spaces. And hence, all what we know about topological spaces can be used for these kind of spaces. In particular, we may define what does mean a complete norm space. Yeah, it's a norm space which is complete with respect to the metric generated by the norm, and a complete norm space is called a Banach space. In a similar way, a complete inner product space is called a Hilbert space. Okay, so now there are two objects, inner product or a norm. Any of them allows to combine topology and linear structure. Okay, so just recall some further definitions. We still just repeat some basics. So let X be a vector space, A a subset of X. The smallest subspace, so the smallest linear vector subspace of X containing the set A is called the linear span of A. And this would be the notation for the linear span of a set A. And if X is a normed space, then the small, so that is, we have a topology, not only linear structure, but also topology. If X is a normed space, then the smallest closed subspace containing the set A is called the closed linear span of A. And it is nothing else but the closure of this set. And it is, notation is the closure of the set span A. Okay. So once again, if we have a norm, we can combine linear structure and topology. In particular, topology means that we can discuss completeness, closed and open sets, etc., etc. That's why this word appears. So a couple of procedures. So let we have a finitely many normed space, then we can consider a finite product of them. This finite Cartesian product consists of like vectors of this type, each coordinate from its own vector space. And it is again a norm space with a natural linear structure, component-wise operations, and with the following norm. So this is a kind of one norm, like L1 norm, or how to say it. So the norm of X is just the sum of norms of its coordinates. And each coordinate, the norm of each coordinate is taken with respect to the corresponding norm. Okay, the space, this norm space is also called the direct sum of norm spaces x1, xn. And this is the notation for this space. Okay. If we have not just norm space, but inner product spaces, so if xi are inner product spaces with inner products, then again their finite Cartesian product is again an inner product space, and the inner product is defined again coordinate-wise, so to say, so in obvious way. And this inner product generates the norm. So this norm will look like this, but this norm is equivalent to this norm. And if all xi are complete, then also the Cartesian product is also a complete norm space, or respectively inner product space. Okay. I guess that this all is known, we just repeat. So may I go further, or there are questions?
Yes, please.
Okay, one more procedure, complexification. So if we have a norm space over real numbers, its complexification is defined as follows. So XC is a space of elements of this view, where X and Y elements of X. And we may create the operations in this set. So it's at the moment this is a set, and now we create vector addition and scalar multiplication with scalar. So vector addition is obvious, like z plus ev. So you add this and you add this, and you obtain again an element. So vector addition is obvious. Multiplication with the scalar is given like this. Now scalars are over C, the complex numbers, and they are given in this by this formula. Okay. If X is R1, then you just get complex numbers here. And the norm on this set XC is defined as follows, again as a sum of like coordinate-wise norm. And then the statement is that this guy is now a norm space over complex numbers. So starting from a norm space over R, we can always construct its complexification, which is a norm space over C. So when we speak about LP of omega, and I don't speak about which field we consider, R or the C, we may always say that we consider R, and if it is not enough, then we make a complexification and we consider C. Okay, I guess this is also known, and we can go further. Oops, what has happened? Yes, so if X is an inner, sorry, if X is an inner product space, then its complexification is again an inner product space where scalar product is given in this way. Yes, so xy, so xu, y and v is here with plus, pay attention. And then this is with plus, so this is with plus, and this is with minus. This is to make this sesquilinear. This is to make this guy sesquilinear. So exercise for you to check that this definition really provides us with something which is the inner product over C. Again, so you see the field, so we consider the field R, but if we need more, we make a complexification. Well, we go further, and one more remark. So I just recall the definition of the norm and say that if a mapping satisfies everything except this one, this mapping is called a semi-norm. So if this is not the case, that is, if the norm of X equal to 0 does not imply that X is a zero element, zero vector, then this mapping is not a norm, but this guy is called semi-norm. We will discuss these objects later on, but at the moment, just the definition, so to say. Well, and one more thing, recall from linear algebra, what is basis in standard linear algebra? It is also called Hamel basis. So a Hamel basis of a vector space is a subset of elements of this vector space such that every element of X can be represented as a finite linear combination of the vectors E lambda from this family. And this representation is unique. So please pay attention. So here the word finite is crucial. And then Hamel dimension of a vector space is equal to the cardinality of a basis of the vector space, of a Hamel basis of the vector space. Okay, this is just to recall you what we had in linear algebra. Now we go further. And let us discuss the situation in finite dimensional normed spaces. abstract finite dimensional norm spaces. So theorem 312, let X be a finite dimensional vector space, then all norms on X are equivalent. That is, for any two norms, P and Q on X, there exists constants, small c and big C, such that we have this inequality for all elements X in our space. Well, I want to prove it, or it is obvious and we don't want to prove it. It's up to you. I mean, I wanted to prove it, but I see that we have not that much time, so it's up to you. Do we want the proof or not? Okay, since you don't answer anything, let me prove it.
Yeah, it's pretty standard, but I'm not sure if I can recollect it
Yes, yes.
spot on.
So let us do it, and then I get probably it will be the last thing for today, but nevertheless, let us do it. So we are in the finite dimensional situation, and it is known then there is a basis for a finite dimensional vector space, and this basis has finitely many vectors. So let EK be a basis Hamil basis in X. That is, for any element X in X, there exists a unique amount of elements x1, xn, which are elements of our field K, such that X is uniquely represented by its coordinates with respect to this basis. Now consider the mapping P, which maps X into non-negative numbers. And how it maps? So X is mapped onto P of X, which is absolute value of x1 plus etc. plus absolute value of xn. So we take any X, we consider its coordinates in this given basis, and then P of X is just absolute value, sum of absolute values of coordinates. So it's one norm, yeah? Or L1 norm, if you wish. So the statement is that this is a norm. Then P is a norm on X. This is an exercise. And it will be kind of a reference norm. So let Q be another norm. So let big C be given as follows. It is maximum over K from 1 till n, Q of EK. EK is a given basis, which is fixed. Then, so we will compare Q with P. So Q of X, this is just Q of, I insert the representation of X in the coordinate form. And now I use the properties of any norm. So absolute homogeneity and triangle inequality. This is just the sum, K from 1 till n. Absolute value of xk times Q of ek. But this is just smaller or equal C, sum of absolute values. But this is just C times P of X. So first inequality is obtained for specially chosen reference norm P and any other norm Q. Okay. In particular, so using this, In particular, absolute value of qx minus q of y is smaller or equal, we use triangle inequality, q of x minus y. And this is smaller or equal, so using this inequality which we have already obtained, this is smaller or equal than c times p of x minus y. What does it mean? This means that the mapping q, which is a mapping from x to real non-negative numbers, is a Lipschitz mapping, or is a Lipschitz function, Lipschitz function on the space X. It's a norm space with a norm P. So with respect to this norm P, we have that this mapping is Lipschitz with, this is the Lipschitz constant of this mapping. And since the function is Lipschitz, then this is a continuous function. Okay. Okay. Moreover, I wait until you are finished. Are you finished?
Please give 10 more seconds.
Yes. So Q is a continuous function in this space. And moreover, a unit sphere is a compact set in this space. This is what I'm going to write down in the next slide. Yes? So may I go?
Yes, please.
Moreover, the unit sphere, let me call it S. This is the set of all x's in X, such that P norm, so P norm of X is equal to 1, is compact in the space X endowed with the P norm, with the norm given by this P. So how to show it? So it is enough to show that this is a bounded set and that it is, that it is a closed set and the set is totally bounded. But to show that this set is totally bounded is very easy because, well, I just use the picture which I have already shown you. So now let it be my finite dimensional norm space X, then the unit ball, so unit ball in this P norm, it's just this cube. And how to make epsilon net for any epsilon for this cube, we have already discussed. So the unit ball is totally bounded and closed, and then unit sphere, which is just a boundary of the unit ball, is also closed and also totally bounded, and hence compact. So we know that the unit sphere is a compact in this space, and we have a continuous function. Hence, this continuous function Q attains its minimum, global minimum, on S So let small c be exactly this minimum of q of x over all x in this unit sphere. We have that this constant c is strictly positive since q is a norm. Yes, so q of x is equal to 0 if and only if x is equal to 0, but this guy does not belong to the unit sphere. Hence, 0 is not attained on the unit sphere. And hence minimum, which is attained, is strictly positive. It's clear?
Yeah, because otherwise we would have a non-zero element,
Yes.
norm of which would be 0.
Yes. Yes. Moreover, for any x which is an element of our set vector space, but non-zero, we have that x divided on p of x. So p of x is a number. 1 over p of x is again a number, non-negative, strictly positive, because we consider only this case. So we can multiply the vector with this number, 1 over p of x. So this element belongs to this unit sphere. So unit sphere with respect to the norm p, yes? And hence, q of x, now I use the properties of a norm, for any norm, is equal to p of x times q of x over p of x. So I just used absolute homogeneity of any norm, in particular the norm q. But this is an element which belongs to S. Hence, this thing is bigger or equal C. Yeah, so this guy is bigger or equal to small c. Hence, we have this inequality. Okay, for x equal to 0, the inequality is also true, because for x equal to 0, we have 0 here and 0 here. So everything is fine. So therefore, for any x in x, we have this inequality. Small c p of x is small or equal q of x, small or equal big C of p of x. So we have compared any arbitrary norm q with a fixed reference norm p. But then we can compare two arbitrary norms with each other using the transition to this reference norm p. So we compare q1 and q2 with the reference norm p. We obtain the corresponding small c1 and c2, big c1 and c2, and then playing with them, choosing their maximum and minimum, we compare two arbitrary norms, q1 and q2. So we have proved the statement. Is it clear with the statement?
Yes, nice proof.
Yes, I think like the more classical one is when we show that every norm is equivalent to the Euclidean norm. So, and this is more like in style of functional analysis.
Okay. Good. Let me just list some consequences of this statement. So we have this nice statement. So what follows from this? So remark, so the space xp endowed with this reference norm P in the above proof is a complete space. This is an exercise, but you can show it rather easy. But having this result and having the theorem itself, we can conclude the following. Any finite dimensional norm space is complete. Yeah, it is complete with this norm, but any norm is equivalent. So it is complete in any norm. And also any finite dimensional subspace of an arbitrary norm space is what? So any finite dimensional subspace of an arbitrary, probably infinite dimensional norm space is itself a finite dimensional norm space, and hence it is complete, and hence it is closed. So this is what is used in the sequel. So any finite dimensional subspace of an arbitrary norm space is closed. Okay. So further conclusions, all closed balls and spheres in a finite dimensional norm space are compacts. Yes, because we have shown that a unit ball or a unit sphere, it is a compact set here, and hence in all equivalent norms as well. So all closed balls and spheres in finite dimensional norm space are compact. So that's why in a finite dimensional norm space, compact space, it is the same as closed and bounded. Yes, because it is exactly what we have in this situation. Yes, again, coming to back to this picture. Bounded means that there is a ball where this set can be immersed into. And then ball looks like this, and then we have shown that this bounded set is actually totally bounded in this P norm. So we have this, and I guess, yes. The next question, so we have clarified everything what happens in finite dimensional normal spaces. Now the question, what happens in general case, in particular when our norm space is infinite dimensional, but I guess we discuss it next time. Now, are there any questions? Okay, seemingly no. Then I stop the recording.